Bismillahirrahmanirrahim. Assalamu alaikum. This is Dr. Noshin Tariq Siddiqui. We were doing pharmaceutics, course number 315. Under the subject of pharmaceutics, we were doing the processes of extraction. We have done numerous processes and we were doing the liquid-liquid extraction processes, in which we were, I was discussing the principle of extraction. I'll repeat from the main heading because yesterday we got offline due to our poor internet connection, but now I'll describe you once again from the principle of extraction. I'll only read that and I'll start explaining from where I've discontinued. Okay, the principle of extraction, solvent extraction depends on a favorable distribution of the solute between the solvent and the feed stream. That I've described you, that the solvent extraction, it depends upon the favorable distribution of the solute, means how much the solute is distributed between the solvent and the feed. Feed is what from which you are basically extracting out the solute. The two important parameters which fix the number of extraction stages and the solvent usage are the distribution coefficient and the selectivity factor. The major point in this is the two important parameters which should be keep in mind are which are distribution coefficient and selectivity factor. The distribution of partition coefficient K is defined as CR divided by CE. What is CR and CE? Where C refers to the composition of a component in any consistent convenient units, and the subscripts E and R refers to the extract and raffinate phase respectively. The raffinate and the extractive phase, the ratio is known as the partition coefficient. A high value of K is required for the components to be extracted. This determines the quantity of solvent required to affect the recovery. Ideally, K is dependent on the concentration of the solute and the ratio of extract to raffinate phase. If the value is high, the value should be high for the components to be extracted. So it gets, it gets into the raffinate basically from the extract, or it should be required for the to be extracted. And the separation selectivity factor S is defined as, while the selectivity is defined as K1 divided by K2, where the subscript 1 refers to the component be preferentially extracted and subscript 2 refers to the component to be preferentially retained. The one is K1 divided by K2. The component which is extracted is preferentially extracted is the concentration of 1, and the component preferentially it should be retained is 2. The separability of component 1 from component 2 increases with increasing separation factor. When the separation factor increases, the separability of the component 1 from 2, of course, it increases. A high value of S indicates the potential for a high degree of separation in a small number of extraction stages. If you get a high value of S, it means you will get a good separation within a small stages of extraction. You will not be needing too many stages of extraction, and you will get a good separation if you get a high value of S. A paper of this I was referring yesterday, I was discontinued here, that there was a paper where they defined or indicated the relative values of 3 different extraction procedures. Those are fractional distillation, extractive distillation, and liquid-liquid extraction. How these 3 are similar? They say in that paper that if these relative volatilities and selectivity factor, if these are in this value, then these processes are said to be same or similar. How? If the relative volatilities of the 2 immiscible liquids or the 2 phases is 1.5 while doing fractional distillation, if you are doing extractive distillation and the relative volatilities is 2, and if you are doing liquid extraction and you get the selectivity factor of about 6, then these processes are somewhat similar. Now, the choice of solvents, I have only given you the main points. Now, some description. The choice of solvent is influenced by many factors, some of which are listed below. These are, number 1 is high selectivity. The ability of a solvent to extract a component or class of component in preference to other means it should be high selective. This factor will determine the number of extraction stages required. If you get a high selectivity, if the ability of a solvent to extract a component, class of component is, it has a higher ability to extract the component, then it means it has higher selectivity and you require less stages of extraction because you will get your component in 1 or 2 stages. Okay. Distribution or partition coefficient, the ratio of the solubility of the solute in the solvent compared to the feed. Basically, distribution or partition coefficient is what? The solubility of your solute, the thing which you are extracting out. How much it is soluble in the extracting, the feed and the solvent. Okay. This factor will affect the selectivity and the amount of solvent phase required. When you know how much your component is distributed, this factor will, affect the selectivity of because if you don't have a good partition in your solvent, then you will not use that solvent. If that is not good enough to carry or to absorb or to get or dissolve the solute, then there is no point from the feed, then there is no point for the selection of that solvent. So and also the amount, because there is a certain because when the component will only dissolve in the solvent when it reaches to the equilibrium state. So you'll require to either remove that solvent and reuse it by making it, devoid of or extracting out your particular solute, and then you can use it again. So this factor will affect the selectivity and the amount, how much solvent you require for the extraction. Density, the greater the density difference between the feed and the solvent, the easier it will be to obtain two-phase separation, because the two phases, they are made because of the difference in densities. So the greater the density, the greater will be it will be easier for to obtain two-phase separation. Viscosity is again very important. A high viscosity will impede both mass transfer and separation of the phase. A low viscosity is desirable. If you have a high viscosity of both the phases, then it will be difficult for them to keep separated as a separate phase. So you need a low viscous liquid, and whose say less than 10 cp is the desirable. Interfacial tension, this affects the setting, coalescence, and mass transfer coefficient of a system. If you have coalescence is set and settling are generally aided by high interfacial tensions, while mass transfer is hindered. Coalescence is actually binding of the components. If you have solid components around, if you have high interfacial tensions, the coalescence or the grouping of compounds will get easier. So you don't want that. So if you have high interfacial tensions, the coalescence and settings are generally aided, while mass transfer, the transfer of mass will be hindered, because the coalescence will form, or the sort of lumps are formed. Okay. Volatility, the solvent is likely to need to be separated from the solute and or the feed If this is to be done by distillation, the volatility should, where possible, be chosen to allow the separation to be easily affected. Volatility, of course, the solvent is likely to need to be separated from the solute or the feed. If it is volatile, then it affects your separation, because you need your solvent to be there, but if it gets evaporated, then you cannot get your desired or desirable extraction. Stability, the solvent should be able to process condition in order to minimize loss by degradation and generation of further impurities. The solvent should be stable. It should not get destable, or it should not be degraded, or it should not generate degraded, because if it gets degraded, it will generate further impurities which will affect your extraction process, and you will get not only your final product or the desired product,